This is the second part of my video presentation on ultraviolet visible spectroscopy. And picking up with where I left off in the first video, we saw that for compounds that contain no pi or lone pair electrons, the valence electrons in such organic molecules are located in sigma bonding orbitals. And so the lowest energy electronic transition that's available for those electrons is from a sigma bonding to a sigma star antibonding orbital, which has a relatively large energy gap. And so the wavelength of a photon of light that is capable of causing that transition is relatively short. In the case of ethane, it was 135 nanometers for its lambda max. And that means that that transition is outside of the range, which from about 190 to 700 nanometers, where most ultraviolet visible spectrometers operate, and so those compounds are not UV active. So let's take a look now at compounds that have unconjugated pi electrons, and of course a very simple example of that would be ethene or ethylene, which has one pair of pi electrons, of course. And we'll recreate our energy level diagram for these transitions. And so recall for ethane, we've got, and we'll look at the carbon-carbon bond, we've got a couple of electrons in a sigma bonding orbital. And so the transition, the lowest energy transition in ethane, the saturated molecule, would be from the sigma bonding to the sigma star antibonding orbital. So now for ethane, the difference in the carbon-carbon bond is that we have two bonds. We've got a sigma bond, and we've also got a couple of pi electrons now in the pi bond. And so now we have a much lower energy transition from a pi bonding orbital to a pi star antibonding orbital. And this would be a good place to introduce a couple of terms that are very common when we're talking about these sorts of transitions, and that is HOMO and LUMO. So HOMO is the highest occupied molecular orbital. And so in ethene, the HOMO would be the pi bonding orbital. The HOMO in ethane would be the sigma bonding orbital. And the most likely transition is from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. And that's given the term LUMO. So for ethene, the lowest unoccupied molecular orbital, the LUMO, is the pi star antibonding orbital. And so the transition we'll be looking at here is now a pi to pi star antibonding transition. So in other words, a photon of light is absorbed, exciting an electron from the highest occupied molecular orbital, the pi bonding orbital, to the lowest unoccupied molecular orbital, the pi star antibonding orbital. And since this energy gap is significantly smaller than the gap that we saw for the sigma to the sigma star antibonding orbital, we're going to expect that the lambda max of this transition will be longer wavelength, and indeed it is. So lambda max for the pi to pi star transition in ethene is 165 nanometers. But you should remember that, again, about the lowest wavelength that we observe in most UV spectra is 190 nanometers, and this is not within that range of 190 to 700 nanometers, and therefore molecules that have unconjugated pi electrons, even though their lambda maxes are longer wavelength than molecules with only sigma bonds, they are still not UV active. And this also applies to carbonyl compounds. So the pi to pi star transition in a carbon-oxygen double bond, which of course is very, very common in organic molecules, is also not visible in UV visible spectroscopy. So we've yet to see any compounds that are UV active, that is, that would have any absorption in the typical region for UV visible spectroscopy. And that shouldn't be a surprise given what I mentioned in the introduction to this video, and that is that the only compounds that are UV active have non-bonding electrons and or conjugated pi electrons. So let's now turn our attention to the effect of conjugation, and that is molecules or compounds that have conjugated pi electrons. And I'm going to start with the electronic effects of conjugation. And so beginning with ethene again, I'm going to construct now a series of energy level diagrams for the pi molecular orbitals, the pi bonding and pi antibonding molecular orbitals for a series of compounds that are going to demonstrate the effect of conjugation on the energy gap between the HOMO and LUMO, which of course is the lowest energy transition for these compounds. And again, I'll start with the pi molecular orbitals for ethene. So this is a molecular orbital diagram for only the pi molecular orbitals. So when two carbon atoms come together to form an ethene molecule, you have 2 electrons in a 2p orbital. And when those 2 orbitals mix, and these are on the 2 separate carbon atoms, they're going to form a pi bonding and a pi antibonding molecular orbital. I'll just label that one pi star. And so those 2p electrons will both end up spin paired in the pi bonding orbital. So this, of course, is our HOMO in ethene, and this would be the LUMO. And so our transition could be represented with an arrow thusly. Let's now take a look at a conjugated compound. We'll start with a simple one, and that would be 1,3-butadiene. And so we now have 4 carbons involved in the conjugated pi electron system. And so again, the original atomic orbitals contributing these pi electrons are 2p. And so these 4 2p orbitals will combine now to form 4 new pi molecular orbitals. And the convention that's often used is to represent these as psi. So this would be a psi1 would be the lowest energy bonding pi molecular orbital. And then psi2 would be another bonding molecular orbital. And then the antibonding molecular orbitals will represent as psi star 3 and psi star 4. And so the 4 available 2p electrons end up in the 2 pi molecular orbitals, the psi1 and psi2, and those are what give us these 2 pi bonds. And so the HOMO now is psi2, and the LUMO is psi star 3. And so the lowest energy transition now has a smaller energy difference than we saw between the HOMO and LUMO for ethene. And so for ethene, we saw a lambda max of 165 nanometers for the HOMO-LUMO transition. For 1,3-butadiene, the lambda max is going to be longer wavelength because it's lower in energy. And we're finally in the range that is observable in a UV visible spectrum. So the lambda max for the HOMO-LUMO transition and 1,3-butadiene is 217 nanometers. So let's take a look at one more example here, and that is 1,3,5-hexadriene, which has a more extended conjugated pi electron system. So now 6 2p orbitals will be combining to form 6 new molecular orbitals, 3 of which are bonding and 3 of which are anti-bonding. And again, we'll label these as psi1 through 6. 1 through 3 are bonding. And so our HOMO-LUMO gap now is even smaller. And so the transition the wavelength of a photon that will affect the transition between the HOMO and LUMO for 1,3,5 hexatriene is even longer than we saw for 1,3-butadiene. And lambda max of that HOMO-LUMO transition is 258 nanometers. And so you can see now what the effect of increasing conjugation is clearly on the gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital. This is the lowest energy transition in these molecules, the most accessible one. And we continue as we continue to extend the conjugation in these compounds to get a smaller and smaller gap. And so we have a lambda max of longer and longer wavelength. So let's take a look now at the UV spectrum of 1,3-butadiene. So again, we have a plot of absorbance versus wavelength. I should mention that absorbance is defined by Beer's law, where the absorbance is the amount of light absorbed by the compound in solution. I'll also mention briefly that the solvents that are used for ultraviolet spectroscopy to dissolve these compounds can and do affect lambda max, the position of these absorptions. So absorbance is equal to epsilon times B times C, Beer's law, where epsilon is the molar absorptivity, also known as the extinction coefficient. And the molar absorptivity is a constant for a given compound, and it's related to the amount of light the compound, that solute, absorbs at a given wavelength in a given solution. B is the path length that the light travels through the solution, and C is the concentration of the compound. So concentration is directly proportional to absorbance, which is intuitive. And we'll have our wavelength in nanometers. So starting at about 200, there's no reason to carry this out into the visible portion of the spectrum. So we'll stop at 400, because as is true with most simple organic compounds, 1,3-butadiene does not absorb visible light. And so we're going to see something that looks like this. We get a fairly broad transition that tails off. And the wavelength of maximum absorbance right there is lambda max, which corresponds to 217 nanometers. And this, of course, corresponds to the pi star transition, the HOMO-LUMO transition, and 1,3-butadiene. Now, there's something that might bother you looking at this spectrum, and that is how broad this peak is. If we look at the transition that we're observing here between the HOMO and the LUMO for 1,3-butadiene, this is a single transition, and this we could reasonably expect would give us a fairly sharp peak, but what we're observing here is a fairly broad peak, which is odd. This is much broader than what we see, the sort of resonances that we see, for example, in nuclear magnetic resonance spectroscopy, or even in IR. Most IR absorptions, although those can be broader, are not quite this broad. So, and this is fairly typical of the sorts of absorptions we see for an UV spectra of molecules in solution. So what's going on here? I'm going to reproduce the energy level diagram for the pi molecular orbitals for 1,3-butadiene. And I'll enlarge it a little bit. And I'm going to leave out the original 2p orbitals for the sake of space. And so we now have psi1 bonding, psi2, psi star antibonding 3, and psi4 antibonding. Now, again, the LUMO is here, and the HOMO is here. And so we've got 2 electrons, 2 bonding pi electrons in psi1, and 2 bonding pi electrons in psi2. I'm not going to show those now. And this single transition should give us a sharp absorption peak. But in reality, we have vibrational and rotational energy levels that are superimposed on these electronic energy levels. So notice, remember, the gaps between the vibrational and rotational energy states are much smaller. So there's a whole bunch of little vibrational and rotational energy states for each of these electronic energy levels. And of course, depending on the temperature, the molecule can, or the electrons can occupy any number of these energy levels. And so if you have a transition between a very low energy vibrational state in the HOMO, let's use a different color for that, to a very high energy vibrational state in the LUMO, that transition has a bigger energy gap than the transition from a high energy vibrational state in the HOMO to a low energy vibrational state in the LUMO. So this bigger energy gap will result in a shorter wavelength. So we might be seeing a wavelength here for that transition compared to a longer wavelength for that transition. And so because these vibrational and rotational energy levels are superimposed on these electronic energy levels, there's a significant amount of variation in the wavelengths that are observed, and that results in these broadened absorptions in ultraviolet visible spectra. So let's now discuss the ultraviolet visible spectra of colored compounds. And recall from a moment ago that we saw that the lambda max for 1,3,5-hexatriene was 258 nanometers. And once again, we know from general chemistry that the region of the electromagnetic spectrum that corresponds to visible light ranges from 400 to 700 nanometers. So even 135-hexatriene is not going to absorb visible light and therefore is going to be colorless. So that indicates to us that colored compounds are going to have extensive conjugation, that is, are colored organic compounds. A good example of that is beta-carotene. And so let's take a look at the structure of beta-carotene. I think you'll agree that we can call beta-carotene extensively conjugated. And so we'll now take a look at its UV visible spectrum. So again, starting at 200 nanometers, we'll go all the way to the end of the visible spectrum, the red side, 700 in this case. And it looks something like this. With a lambda max, which is located right there, obviously, equal to 455 nanometers, which is in the visible portion of the electromagnetic spectrum. And one thing I'd like you to think about here is what color of light does this correspond to? And just to refresh your memory from general chemistry, the visible spectrum begins at 400 nanometers. That's the violet end of the spectrum, 700 being the red end of the spectrum. And so this, of course, would be violet to blue light. We all know, obviously, that beta-carotene is orange. I don't know why I use blue here, but beta-carotene is orange. So why is it that beta-carotene, an orange pigment, is absorbing in the blue to violet region of the electromagnetic spectrum? We now have two more types of electronic transitions that are relevant to UV visible spectroscopy to consider, and those occur in compounds with non-bonding electrons, which again, I'll mention one more time, are, for our purposes here, lone pair electrons on heteroatoms, on certain heteroatoms. And there are two possible types of transitions that we can observe that involve non-bonding electrons. And those are from the n non-bonding orbitals that contain the lone pair electrons to either a sigma star antibonding orbital or a pi star antibonding orbital. And both of these, in many cases, in some cases at least, can be observed in the UV visible spectrum. I'm going to give one quick example of that, and that is for the N to pi star transition for the compound 4-methyl pent 3-ene-2-one, which has this structure. And again, we'll observe the N to pi star transition. And so let's look at the UV spectrum for this compound. And what we're going to see is that there are two absorptions in this spectrum. One more intense at lower wavelength and one less intense at higher wavelength. The more intense absorption corresponds to the pi to pi star transition. So it's an electron being excited from a pi bonding orbital to a pi star antibonding orbital. The second absorption here is the N to pi star transition. And so what's happening in an N to pi star transition is that one of the non-bonding electrons in one of the lone pairs is being excited to an antibonding orbital in the pi electron system. Now, those transitions are always lower, of a fairly low absorption, fairly low intensity. And the reason for that is that they are effectively not allowed by quantum mechanics. It's known as a forbidden transition, so it's difficult for that transition to occur and statistically improbable. It does occur, but when it does, it doesn't occur very often, and therefore the absorbance for those N to pi star transitions is small compared to the absorptions for pi to pi star transitions. And so this is the sort of thing you typically see when you have lone pair electrons. I have one last topic to discuss in this video, and that is the substituent effects. And what I mean by that are the effects of substituents, different functional groups, on the absorptions of molecules that contain conjugated pi electron systems. And we're going to start with the concept of chromophores. And the definition of a chromophore is very simply a functional group with pi electrons that absorb ultraviolet and or visible light. And some obvious examples of that would be things like carbon-carbon double bonds, carbonyls, triple bonds, and nitro groups. And the very simple rule that I'd like you to remember is that the more chromophores you have in conjugation, we're talking about pi electron conjugation, the longer the wavelength for the pi to pi star transition. And to give you a few examples of that, we saw that the carbon-carbon double bond in ethene has a lambda max of 165 nanometers. Acetone, which has a carbonyl, has a pi to pi star lambda max of 150 nanometers. Now, when we put a carbon-carbon double bond in conjugation with the carbonyl, the lambda max of the pi to pi star transition moves out to about 240 nanometers. And so the first two functional groups in isolation, carbonyls and alkenes, are not UV active. They do not appear in ultraviolet visible spectra. Putting them in conjugation, we get an absorbance that's clearly visible, an absorption that's clearly visible in an ultraviolet spectrum at 240 nanometers. The second type of substituent I'd like to mention are oxychromes. And those are defined as saturated groups with non-bonding, meaning lone pair electrons, that change the wavelength and intensity of absorbance in a compound when in conjugation with chromophores. Common examples of oxychromes are the following: alcohols, ethers, amines, thiols and sulfides, and halogens, all having non-bonding electrons that can be promoted to pi star or sigma star orbitals. For our purposes, the most important thing to understand about oxychromes is that they increase the conjugation of pi electron systems, and therefore they tend to lengthen the wavelength of the pi to pi star transition of those systems. So we have lambda maxes at longer wavelengths. Interestingly, they also tend to increase the intensity of absorption. And to give you a quick example of that, let's look at the pi to pi star transition, the lambda max for benzene. Which is about 254 nanometers. Now we'll add a common oxychrome to make phenol. That's an OH group. And the lone pair electrons on the OH group, of course, are in conjugation with the pi electron system of benzene. So that lengthens the conjugation. We can just draw one of those resonance forms. There are many others, or several others. And so the lambda max for phenol is 270 nanometers. And so that, of course, has been extended by the extension of the conjugated pi electron system. I'm going to leave you now with the sort of problem you might expect to see on an exam. So which of the following compounds would you expect to have the longest wavelength absorption in an ultraviolet spectrum? So pause the video for a moment and make your choice. If you chose the third compound, you are correct. The reason being, of course, is that it has the longest conjugated pi electron system. So in this compound, we have 1, the carbonyl, 2, 3, 4, the pi electrons in the benzene ring. So we've got 4 chromophores. The ones in the benzene ring really would not be considered separate chromophores. The pi to pi star transition in aromatic rings is a little different than the pi to pi star transition in non-aromatic compounds, but we can consider this for simplicity to be 4 conjugated chromophores, also conjugated with this oxychrome, which is the methoxy group here. So we have this long conjugated pi electron system. In the first compound, we have 2 chromophores, the carbonyl and the carbon-carbon double bond in conjugation with an oxychrome. And then, not in conjugation with that system, we got another conjugated diene on the other side of the molecule. In the second compound, we have an isolated benzene ring. So we'd expect its lambda max to be around 254 nanometers. And then, not conjugated to that, we have an oxychrome isolated by itself, the OH group. And then finally, in the fourth structure, we've got 2 dienes that are isolated, that are not in conjugation with each other, and we've also got an oxychrome that is not conjugated with either of the dienes. So the compound with the longest conjugated pi electron system is the third one, and we'd expect that one to have the greatest lambda max for its pi to pi star transition. You'd also see n to pi star transitions here, but those would be weak. So that concludes my discussion of ultraviolet visible spectroscopy. If you have any questions, please let me know.